Good morning. Myself P. Vanita, working as an assistant professor in the Department of Electrical and Electronics Engineering. Today we are going to discuss Unit 2, measurements of parameters in electrical systems for the subject measurements in the instrumentation. First, let us understand what an instrument. An instrument is simply a device used to measure the magnitude or value of a physical quantity. When we talk about electrical measuring instruments, these devices work based on electrical principles to measure quantities like current, voltage, power, and energy. There are two basic methods of measurements: direct method and indirect method. In indirect method, we measure the value directly using an instrument. In the indirect method, we calculate the value using related measured quantities. Now let us move to the classification of instruments. Instruments are broadly classified into two types: absolute instrument and secondary instruments. First, absolute instruments. These instruments give the value of the quantity in terms of physical constants of the instrument itself. They do not require calibration with another instrument. For example, is the Tanset galvanometer. Next, secondary instruments. These are commonly used in practice. These they need a calibration using an absolute instrument. The value is determined by reading the output shown on the instrument scale. So, in practical laboratories and industries, we mostly use secondary instruments. Now, secondary instruments are further classified based on the effect of the electric current or voltage used in their operations. First, magnetic effect used in ammeters, voltmeters, and wattmeters. Second one, heating effect used in certain types of ammeters and voltmeters. And third one, chemical effect. It is used in DC ampere hour meters. Fourth, electrostatic effect. It is mainly used in voltmeters. And fifth one, electromagnetic induction effect is used in AC ammeters, voltmeters, wattmeters, and energy meters. So, depending on which physical effect is used, the instrument design changes. Now, we classify instruments based on how they operate. First, indicating instruments. These instruments show the instantaneous value using a pointer moving over a scale. For example, ammeter and voltmeter. Second, recording instruments. These instruments continuously record the variation of a electrical quantity over time. Third one, integrating instruments. These instruments measure the total consumption over a period of time. They do not show the instantaneous value. Examples include ampere hour meter and energy meter. So the difference is indicating shows present value, recording shows variation, and integrating shows total value. Now let us understand electromechanical indicating instruments. For proper working of such instruments, three forces are required. First one, deflecting force, controlling force, and damping force. These three forces ensure proper movement to accurate reading of the pointer. Deflecting force, when there is no input signal, the pointer stays at zero. When when an electrical quantity like current flows, deflecting force is produced. This force moves the pointer always from zero. So basically, the deflecting force is responsible for moving the pointer according to the input signal. Now, if only deflecting force acts, the pointer will keep moving will not stop at a fixed position. So we need a controlling force. This force acts opposite to the deflecting force. The pointer stop at a steady position when deflecting torque equals controlling torque. Also, when the input is removed, the controlling force brings the pointer back to zero. So it is ensures stability and correct measurement. One common method of producing controlling force is the spring control method. Here, two springs are attached to the spindle. The spindle is mounted on jeweled bearings. Dual bearings to reduce friction. The rings are placed in opposite direction to reduce temperature errors. Usually, the rings are made up of phosphorus bronze. In this system, the deflecting torque is proportional to current. When controlling torque equals deflecting torque, the pointer reaches a steady position since deflection angle is directly uh, proportional to current. The scale is uniform. That's why the spin controlled instruments have a linear scale. Thank you.